Hello everybody. This recording is about using Risa connection and verifying with our hand calculations a simple connection for a building. So we discussed already that we have different types of connections, tension members, we have connections for compression members and flexure or bending members. In the lecture, we discussed that the bending connection from a beam to girder or a girder to column, these are because they're bending elements, the connection part is going to transfer reactions from beams to the supporting elements. Because of the direction of the reaction force downward, the connection elements are going to be under shear. That's why this simple connection is called shear connection. When we do connect, you use shear connections in W shapes. Typically a W shape, wide flange is what we use for bending members. Since web of the W shape is in charge of transferring the reactions or shear forces, we do that by connecting the webs directly to each other, to the support. If it is a girder, to the web of the girder or the flange of the girder, but it is through the web of the beam. Now, if we have some eccentricity in our connection, there is definitely an eccentricity you see here. The reaction is here to the column, so the column here is going to experience some bending moment there too. But that's not what the beam is designed for. So if we don't consider it in the beam design, those eccentricity will add in some stress on the elements. We are not including in our calculations. Okay, so in simple connections, what we consider, I think there are two other different, yes, let me show this one basically, because this is beam to a girder one, right? So we typically have to check all the parts, make sure they can adequately carry the loads, right? We know that in bridges, a very critical type of failures has happened in connections. And that is not just the bolts. The bolts used to be like very old school, rivet kind, and not high strength. But with the modern construction nowadays, we have higher strength bolts. You see, even if the FOI here for a material is 50 KSI, for bolts, that's way higher, 65 KSI, it's high strength. So the bolts are not concerned and they're not critical in design of connections. Usually what governs the design is some other things like geometry. First of all, geometry should be, we have to make sure that doesn't cause crippling or what we call point load into the web, so it can be distributed through the web. So even though we need like two bolts can carry the entire reaction, but we need to distribute it over the web more evenly, so we employ more, like 3 or 4. Okay. The other part that we have here is the angle. Typical connection is a double angle on either side of the W section. And we can have, and very common one is that we have basically welding on one end and bolting on the other end. Okay, so that pretty much speeds the construction time and everything. You know, just count number of bolts required for this one connection. Look at it, 8, 12. Right? Only 12 bolts are used in this simple beam to the girder connection. So that's also one of the cases I wanted to discuss. So when we design the beam itself, we already designed it for bending moment, which is going to cause maximum bending moment at mid-span. We also considered the shear, which is reaction, and we checked with table 3.2 if you remember, which is basically equation depends on the area of the web times the strength that can handle. Okay, and though in connections we also consider that we know we're going to have shear here, but net area is going to be the net area is way smaller than the gross area, so it may be critical. The reduced area under bolted connections where we have holes will be more critical. That's not the concern with the welds, right? Because you are using the entire section there. On top of that reduction area due to the holes, we do have what we call this top part of the W shape, which is the top flange, and some part of the web removed. So you have also reduction in the strength due to that, which we in selecting the initial member size we did not consider, and we do that usually in the connection design part. Okay, so that's why we need to check multiple things, and that's what we did in the example, and I'm going to keep doing that after I finish my calculations in OneNote. One is that we need to check the strength of individual bolts. We know their strength, if they're on double shear or single shear, what's their diameter, okay, what type of bolt we have. Second, we need to check the strength of the angle right here, because it has thickness and everything, and angle is going to transfer the forces from each of these bolts, right, from the member itself to each of these bolts, and then from each of these bolts to the angle, so angle has to transfer to the other bolts on the other side, correct? So bolt is sitting on your angle here. It's going to cause tear out or bearing on the angle itself. So we have to check also if the bearing of the bolts on angle is fine, as well as on the other side, we have angle on here, and on the other side, if they're not same size, same number of bolts, as well as the beam itself, web of the beam. Okay, so what I showed you in last lecture was that table 10.1 gives you the strength directly based on number of bolts and your angle thickness, right? So that one is basically does majority of the checks for you. The bolt itself, tear out and bearing limits on your angle, as well as the block shear strength on angle. So it does it, but what it doesn't do is it doesn't give you the strength, reduced strength of the what we call beams. So let me show you here the beam itself. If I go to members and LRFD results, and I have girder and beam, so those are the members and these are the components, right? So you can obtain all those information from here rather than going to table 3.2 to check. Okay, so I have clip angle, block shear at girder, at beam, rupture at beam, right? So that's one of the things we have to check. But basically, rupture is what we do usually when we design the member itself. Or for connection, it's not a problem. What I want to is bolt bearing on beam. This is essential, that bolt bearing on beam usually is not done in table 10.1. It's not. The reason is we don't know how much the beam is going to be cupped. We don't know what is the edge, the distance from the beam. It's hard to, the fittings here, if I want to show you here, so these typical LE is the edge distance from the center of top bolt to the edge of the clip angle. That's typical. We use them from, of course, this is constructability, right? 1¼ of inch or 1½ inch if your bolt is bigger size, okay? So these are typical numbers that we want to comply with, but it's hard to round this number. Let's find out exactly what's the center spacing from the top bolt to the top of your flange, right? In this case, I made it so that it's like exactly 3 inches, but that will depend on, right? That will depend on how much you cope here and how much, because of the girder size, girder thickness and everything. So it will vary. That's why table 10.1 does not provide bolt bearing on beam. So in my hand calculations, I will check the bolt bearing on beam, and I expect you guys also to do that in your project calculations. But don't do the calculations for bolt bearing on clip angle. Instead, you can use table 10.1. Why? Because we are repeating the same thing. But for the sake of example, I will show everything. So you see with hand calculations, we have to check all 3 of the bolt, angle, and web, see which one will govern. Of course, Risa does a bunch of other checks here. You see like bolt prying and stuff that we are not going to discuss. Okay, so let me get started with doing an example. Here I have a W section, W18 by 35, correct? And let me just go to the OneNote now and show you. I'm going to do the analysis here, and the analysis is on shear connection, of course. So this is a flexure bending member, flexure member, but because it's only transferring the reaction to the support, we call it shear connection. So bolts are all A325N, not included threads are not included in the shear plane, and in standard holes. And we know what is the material for ASTM for angles and beam. Okay, so now we also have the connection detailing. So 1¼ of inch is the typical edge distance in the clip angle, in the angle to the top, and 3 inches is typical spacing for center to center bolts. So this distance is calculated here, but it's hard to accomplish in Risa. We're gonna do that. I'll show you why. It's approximate. In other words, in this example, I just copied it from textbook, and which was one of the problems, I believe. That 2 inches it's hard to do. You know, you have to either know how much you're coping, or this distance from the center of the bolt. Okay, in this case it's 2 inches. We're going to try our best so that we cope it, that we end up with exactly that edge distance of 2 inches. The horizontal edge distances, LEH, is 1¾ of inch. Typically that's more than 1½ inch, because we want to make sure that we can accomplish the tightening of the bolts with the wrench and so on. Okay, so this W18 by 35. We are not checking the girder strength. It's similar to the beams. It's same thing. It's really tedious calculations. Here we assume that the girder is going to handle it safely. Okay, so the step 1 is going to be finding out if the bolts are okay. All right, so first I'm going to do hand calculations, and then I'm going to show you the table 10.1. That makes everything easier. And in here, bolt bearings. First check bolt bearing. So strength of the bolts, right? Bolt bearing. Am I right? Bearing. So where do I obtain that? For that, you have the handout from last semester. We had strength of 1 bolt, and 1 bolt was a function of phi r, and small letter n was a function of its nominal shear strength which is provided in table J31, I believe. It's like 65 KSI or so on for bolt types, times area of the bolt, right? And then you have to multiply this number by number of bolts, as well as if it is in shear, in double shear, you have to multiply it by 2 or 1, okay? So it depends on that one too. Okay, so in this case, the bolts are under double shear, correct? Because we have double angle. Double angle, you just go to here. Your bolts are under double shear because the bolt is touching the shear plane twice on either side of your member. So it's going to transfer that to the angles, right? And that's divided by 2. So that's why you have to multiply that by 2. It's that, or you can use table 7.1 to obtain the shear strength of one bolt. Okay, if you go to table 7.1 and let me give you the information for that. This is A325N, so it's going to be group A. I mentioned that if you forget, you can find that on manual and A325 325A, and it's gonna be, okay, I have to maybe pause here. I don't know how to pause in. Okay, yeah, here. Table 7.2 is on page 7-23, right? So you have group A, A325, and you have the diameter. So the diameter of the bolt is given in the example. That is, what is the diameter of the bolt? With 3/4 of inch, right? With 3/4 of inch, if you have threads included, F and V would be 40.5. So you can multiply that by area of the 3/4 of inch bolt, which is 0.442, right? Or just get it from the formula. But it's double shear multiplied by 2. It's going to be 35.8. Okay, so 35.8 from the manual using this, and the diameter phi equals to 3/4 inch, right? From all that, and then we know it's double shear. The strength of one bolt is going to be 35 point, what did I mention? 35.8 or 17.9 times 2, 35.8 kips. How many bolts we have? We have 4, so phi Rn will be 4 times 35.8 equal to 143 kips. That's the shear strength of bolts. Our goal in this analysis problem is to obtain the strength, how much shear this connection can handle. So we have to calculate all of them and then see which one governs, and based on that, basically go based on that, right? Whichever governs. So this example 2, I will just add the solution. I'm not going to go over the recording for that. So second part is bearing on beam web. Check. Bolt bearing itself, not itself, but bolt bearing where? On beam web. Beam web. This is W18 by 35. So we have the thickness of the web That's why I please ask you guys to write these parameters as well as the f of y and fu. Why? Because when you check with the clip angle, I see you keep doing the same mistake and plugging 65 KSI. But if you write it on each step, you won't make that mistake. That's 50 KSI and 65. And the thickness for the web would be, this is 18 by 35.3 inches. It's given. Okay. All right. So now I feel like I'm slanted. So okay. So now let's calculate the formula. Right. That's the formula I gave last on the lecture. So phi Rn equals to, oh, this is the summarized equation that I gave you. For each individual bolt, you can write this, but we can write that for summation of all of the bolts, phi times 1.2, f of u times thickness of the web, of the member, right, times minimum of, this is the formula I gave you. One of these two is going to govern, right? LC1, LC, and 2 diameter of the bolts. Okay, so for LC, I need to consider what is the edge distance and what is the clear distance and what is the diameter of the bolt. Okay, so that's essential. Let me just bring your attention here. I'm going to go to D view, right? Edge distance. Does this make sense? Is this the one I created for this class? Yes, it's W18 by 35. The angle is, I'm going to check if I made this all complying with what we have. Then let me show you how did I do that. I created a new connection, and I can show you the same thing, to do it same thing. And that's like, you can go to new connection on your Risa. Sorry. File, new connection. Okay. And you can call it, this is a girder to beam, and its connection is clip angle. But it's on one side shear, right? I don't care if the girder is interior or in exterior. I'm just checking this simple connection, shear connection here. And I call it a connection 4, right? By default, this is Risa's default one. So they weld the clip angles to the beam. It's easier in shop. Okay, so let me just go and edit that. You see that when I click on my angle, this option gets activated, and then I can click and change that to bolted. So it's now all bolted. My member, I can change that. It's W16 by 36, it's default. I can change that to 18 by 35. All right. Now I have 4 bolts. What's the diameter? If I want to change that, beam bolts, I have the option to do it here. 3/4 of inch, group A, and number of rows, bolts per row, there are 4, right? You can change and modify them all in here. And longitudinal spacing between each is 3 inches. Is this slip critical? No, this is a bearing type. It's not for bridges. Okay. Girder doesn't matter for me, right? I don't care. We're not checking here. So if you're checking in analysis problem against a given force, like your beam to girder connection, you know what is your ultimate reaction, VU. You can give that number over here and ask Risa to check if it's less than your phi Rn, right? If you don't have it, just leave it. Don't give anything, right? That's the option. So in this example, we are trying to obtain it. So that number doesn't matter. What is it? So I can just change it to a small number so I don't see that failing thing. Because it's analysis, it's not design. Okay, so I think I gave everything here. I'm going to go to 2D view for, this is the beam, that's the girder. And if there's anything in terms of this edge distance, I'm going to modify that. In that problem, LC for the top bolt to the beam web, that is 2 inches. You can see that, right? 2 inches typical, right? Oopsie. It's from here to the web's top. That's 2 inches. And then this guy is 1¼ of inch. That one is on for the clip angle. So here for clip angle, I have 1½. So I'm going to modify that by clicking on it to 1.25 inches. And then this other number indirectly is going to be calculated. If I have 1¼ and 1½ here, which Risa gives, if you deduct this 1.01, you can obtain that, you can obtain what would be the distance from here to the top of the web. So in this case, 1.25 plus 1½ is going to be 2.75, correct? If I deduct 1.01 from it, this is going to be exactly 1.75. So it's not 2 inches, it's 1.75, but it's fine. Why? In our hand calculations, this is very accurate, all right, in what is Risa showing. In reality, manual says that you need to deduct 1/4 inch tolerance for the web cupping. So it's just like for punching in the bolts that we said, let's add in another 1/16 inch for the tolerance imperfections in the punching process, making holes, so that we take out that part in getting the strength of the web here, okay? So manual says to take out that 1/4 inch. You can do that as well. Okay, so that is, I said, what did I say? It said 1.5 or 2 inches in the example. You can make it 1.75 here, just to take it out, because Risa is so accurate here. If I want to do hand calculations, I'd better use based on 1.5, 1.75, and so does Risa. Okay. All right, so I'm going to come back here. You see that 2 inches, it's the approximate. It's approximate. I am going to make it 1.75. And in Risa, I'm going to make it also, but in Risa, I'm going to make it exactly 2 inches. So it doesn't matter. It's going to be a little bit different, okay, over there. Okay, so my edge distance, I want to copy that part here from Risa. And how do we, that's the web. Okay, I want to just look at, oh no, that's going to be the front view, and that's showing the girder, not the beam. I want to only show you the beam, okay? And that's, you see that LC edge distance, it's from here to there. I just calculated, I said, what was it in the calculator? It was 1.75, 1.74 based on what is you see here, okay? 1.75, 74. And that's exactly matches with what I am going to assume. So let me, I don't want to change these. The coping is really something that is, we want to know that distance is usually calculated, this one. Calculated based on what you give here. So it's your option. You want to change that to 1.75 or not. Okay, but this will work for me. Okay. So let's calculate now LC. Okay, how do I do this? I don't know. Let me just copy this part. I want now. So be careful. What the difference is else for LC is I have this edge bolt, and then I have other bolts, right? These are other bolts. Other bolts. For edge bolt, your edge distance, your LC is from here to here, right? And that's clear. So your top bolt is, that's your L LE vertical. LE vertical is 1.74 in Risa. Let me say it's about 1.75 inches here. Because in hand calculations, it says that 2 inches, you have to deduct a quarter of inch for tolerances. 2 inch minus 0.25 equal to 1.75 inches. Okay, that's how I obtain. Okay, so LC H distance for the end or one, bolt number 1. You see last semester we used number 1 here, number 2 for other ones. For that would be 1.75 inches, all right, minus, let me first calculate diameter of holes. Diameter of the hole is gonna add in 1/8 of inch, okay, 1/8 of inch or 1/16 of inch. You know, in Risa, it does add in 1/16 of inch. Bearing on beam, okay, Risa does add 1/16. The Aguirre textbook adds 1/8 of inch. So it's not a big deal here, okay? I'm trying to just show you the, so I'm gonna say this is gonna be 1.75 minus half diameter of that hole, right? This diameter of hole. What's the diameter of hole? It's gonna be 3/4 of inch plus 1/16 of inch. Okay, so LC1 will be equal to 1.75 minus, what is this this value? Let's get this one. 3/4 plus 4 plus 1/16, 1.8125 inches. So I'm going to deduct it from half of this diameter of the hole. This is half, right? So that would be 2 plus 1.75, 1.34. Okay, now I do have also I have to get the 2 times diameter of the bolt, which is what? 3/4 times 2 times 0.75 equal to 1.5 inches. I need to do this for other bolts. Let's get the LC2 for other bolts, the clear distance between the bolts, all right? That's what we call LC2. LC2. That's the typical center to center spacing is 3 inches. I'm going to take out one whole diameter of the hole, and that is minus 0.8125 equal to 2.19 inches. Okay, so I have them. Now for edge, you can write all these. For edge bolt, it's better for me if I do check everything right at the edge. Bolt, edge bolt is gonna be, if I put this, for edge bolt, this value will be VRN. We know reduction factor for shear is 0.75. Okay. Then I'm going to write minimum of these 2 numbers that I want to add in. Okay, minimum of what are those? 1.2. You see these 2. Okay. I do also have another thing, and that's the bolt itself, strength of 1 bolt. Okay, what is the strength of 1 bolt? 35.8. You know, for edge bolt, I have to consider which case is critical. The bolt is weak, or the web of the beam here cannot handle it. So for that, I have to see which one is weaker, and then calculate based on that. This is web of the beam for edge bolt, and that's the strength of 1 bolt. Okay, so strength of 1 bolt was, we just got it, 35.8. So it's gonna be minimum of, let me then write, is gonna be minimum of 35.8 and 0.75. What is the formula? 1.2 T of the W, which is 0.3 inches, times FU, which is 65 kips, KSI for the beam, and FUT times minimum of what? The other two. So which one is here? LC1, 1.34, and 1.5. So for edge bolt, this one will govern. And I'm going to obtain this part. We're going to calculate this part. And obtain, this will be 30. Okay, I don't know. Let me just plug it in. 0.75 times 1.2 times 0.3, 65, and 23.517. Yes, so this part will be 23.52517. So this one governs, right? That's not small. So bolt won't fail. The beam web is the weaker component. 23.52 kips. For other bolts, so I have summarized everything in that formula so it doesn't make you really confused. Minimum of same thing, 35.8, and what changes is everything else is the same. T 65 and times minimum of 1.34 is going to be 2.19 and 1.5. Okay, so which one governs here? 1.5. 2 times diameter is smaller, right? So if you do that, yours is going to be 1.5 instead of 1.32, right? So divided by 1.34 multiplied by 1.5, that's going to be 26.32. So this right side, this number is going to be 26.32. This one will still govern. That's not gonna control, but I did check it just in case. That's for clip angles that usually governs 26.3 kips. So I have the strength of the edge bolt and other ones. So now I can get the phi Rn as a function of all the bolts. How many bolts I have? One edge bolt, 23 plus 52 plus 4 minus 1, 3 times 26.3. So you need to multiply that. You are going to obtain 102.5 kips. So I just checked the beam's web, right? Now I'm going to check the beam's web against what? Block shear. I haven't done that, okay? Block shear is one thing that if you do in your design, you're gonna end up seeing that may govern. So for block shear, if I write that, try to visualize this again in here. Block shear happens, team viewer, okay. Block shear happens on the beam, all right? I wish I could take out the webs, the clip angle and show you. So for the critical failure path for clip angle, I keep saying clip angle, for the web of the beam will be, so I'm checking now, check, what, I did, that was my step 2, right? Step 3, check, block shear on web. Why I should check the block shear on web? Because now I have more bolts maybe than what I assumed in the initial design, as well as I have coped section. So for that, I need to consider what is the critical path, right? Let me draw that with red in here. With red, this is gonna be my critical path, like this, the block shear, okay? So these areas are all under shear. This will be under tension. So I'm gonna show that with blue color. So red means is under shear, blue means is under tension. See, this is going to be stretched, but these are red ones are going to be, because of the bolts and reactions from the bolts, they're going to be slide against each other. So they're going to be shear areas. The formula that we have for block shear, if you recall, it's from the handout. I can rewrite it black color. So phi Rn equals to 0.75 minimum of, and if you guys ordered the manual, there was a simple booklet, I think came with it. These formulas are summarized there too. Fu times net area of the section under shear. Under shear, so Fu a rupture, and 0.6 gross area FOI under shear. So now this is what we had last semester. I'm just doing it. Okay, plus what? Tension area. Which tension area we allow it to reach rupture? Fu times net area under tension. So that is what I'm gonna consider. Minimum of these two plus that, and that whole thing times 0.75. Okay, so which one is going to govern? I have to calculate net area under, first gross area under shear, net area under shear, and then net area under tension. So gross area under shear is easy because this is the entire red area, not take out, don't take out the holes. It's like this area entirely under shear. So that is 3 inches. So 3 times 3 plus that edge distance was 1.75 or 2. Yeah, for shear you can assume. Yes. Okay. So it depends. All right. Yeah, right. From here to here, we calculated that to be 1.75. So you can do that same thing. 1.75. I said, right? Took out that. I'm not taking account in the bolt calculations. Up to you. You wanna go with deducting that. That's totally okay. I'm not sure what did I put it in, Risa. 1.75 multiplied by, oh yeah, plus, okay, 1 plus 1.75. Then we multiply that by the thickness of the web, which is 0.3 inches. All right. I can put this 2 inches just to make it around. Okay, that's fine. It doesn't matter. Net area under tension. Net area to under tension is gross area under tension, shear, and minus, take out the holes. How many holes you have? We have 3.5 holes. 1, 2, 3, and then 1/2 here. So you have to take out 3.5 holes. Diameter of the hole times thickness of the web. Okay, so let's see. Take first one. This one I just calculated based on 2 inches, which won't matter that much, guys. 1.75 plus 9, 10 points times 0.3, 3.22 inches squared. Okay, and net area under shear would be 3.22 minus 3.5. Diameter of the hole is 3/4 plus what? I had it in up there, just got it, 0.8125. Right, diameter of the hole, 0.8125 okay, times the thickness, which is 0.3, will be equal to, if you take it out, and 2.3 inch squared. I calculated. Okay, net area under tension is this blue area. So what is that? Oh, I have to, if I haven't, I have to check that on Risa. And this example says that horizontal LEH is 1 3/4. 1 3/4, right? So I have to make sure that over here, that is also 1.75 inches. So it complies. It's completely the same thing, right? So that's that. Okay, so for an area under tension, that would matter a lot. Okay, yeah, maybe I don't need to just over here, just modify that to 1.75 because I have already highlighted my tension and shear areas and I don't want to miss it. So 1.75 minus half diameter of the hole, 0.5 times 0.8125. All right, times the thickness of the web, 0.3. So the answer is going to be 0.4 inches squared. All right, I have all of them. Let me plug in the formula to get the block shear strength. VRN will be equal to 0.75 multiplied by minimum times minimum of the numbers that's in here. In bracket, I have 0.6. Why we multiply 0.6 F of U? Remember, guys, block shear strength of the steel is 60% of its tensile strength. These are what we determine from tensile stretching of the rod, right? 65. Net area under shear is 2.3. Then this one, sorry, and net area, and should have not put the parentheses there. Oh gosh. Minimum of that, and 0.6 times 50 ksi. That's the strength of web itself, right? Not angle. Gross area under shear, 3.22. Let's calculate, see which one is going to govern our strength. Then add in the tension area, 65 by 0.4. If you plug in, we're going to get about 88. Maybe yours is going to be small, a little bit different because I originally get this one based on 3.3, not 3.22. So it's going to be small a little bit, but this is what I have, 88.76 kips. Okay, now in step 4, I need to determine the strength of what? Strength of this angle, clip angle. Angle is similar to what we do for beam, except that for angle we have LC is different. Check. Bearing bolt, bearing on angle. I'm not checking the block shear on angle, and for that you should write what's the thickness of the angle, what's the F of U and Fy for the angle, as well as, you know, what is LC and LC1 and LC2. Why? Because in angle those are different, right? It's 1 1/4 inch now. So you have to 1 1/4 minus. So if you take it out, it's going to be slightly smaller, and then you can calculate them. So step 4 is exactly similar to step 2. Similar to step 2. And that is given basically this one, and results from step 1 and step 4 is given in table 10.1. So for that I am going to use table 10-1 instead. Okay, I'm going to go to table 10.1 here. Right there, 10-1, and find what page was it? 10-13. Okay, and I have, of course, 3/4 of inch bolt, and I have W18, so it's going to be 10-17 with 3 rows and 4 rows. I have 4 rows. What's the angle thickness? Angle is L. What is that? 4 by 4 by. I haven't given the information for the angle yet. 3/8. So let me give that in Risa. 4 by 4 by with angle 4 by 4 by 3/8. Okay, in Risa you have to give this in every 16th of inch increments. So this will be equal to 6/16. Okay, and you rather than giving 6/16, we give that numerator number 6. So I'm gonna go to Risa, and for my angle, click on it, and then when it's active, I can change that by clicking here, 4 by 4 by 6. So it's equal leg. Okay, so that I did that too in Risa. Now I'm going to obtain its strength, okay? And go to table 10.1. With 4, it gets you the bearing and tear out limits and everything. It also does table 7.1. So it's all summarized here, and see which one is going to govern. So for angle, I'm going to use this number, of course, because I have 4 bolts, not 3. From table 10.1, we obtain what? 4 rows. This is the diameter. This is the f of y. Group A, threads included, standard. And then, of course, angle thickness was 3/8. LRFD strength would be 140 kips. So phi Rn will be 140 kips. What does this number is telling you? That what we obtained in step 1 was 143 based on bolt strength. That is not governing. What governs the strength for here is the strength of the angle. So angle is gonna fail before the bolt because that's less than 143, right? So that's that too. I obtained that. Now I'm gonna go to step 5 and obtain the final number. So which one is the minimum? 140 here. From step 4 we obtained 88. Step 3 we obtained 102. Basically step 1 and 2 can be block shear. No, 1 and 2. No. Step 1 and 5 are the same, okay? Step 2, 3, so I'm going to write here phi Rn will be minimum of 100, not step 2, numbers from not step 1, step 2, and whichever is for beam, okay? Step 3 is the shear on web. Step 2 is bolt bearing on web, right? 2, 3. And 4 is angle, so not that one. Step 2 and 3, 2 and 3, not 4. Okay, so steps 2 and 3, I'm going to write here. And step 1 and 5 are, 1 and 4 are in table 10.1. The number from table 10.1, 140. Okay, and minimum of step 2 is 102. And minimum of step 3 is 88.76. Let's say 88.7. That's step 2. Step 1, 3, and step 1 and 4 are both summarized in there. So minimum of all steps is going to be 88.7 kips. What governs the strength of this connection is the block shear. All right, so let's verify that in our beam checks and clip angle checks in Risa. I'm going to go to the reports. I'm not checking, I'm not designing, so I'm just going to check my numbers. So I have beam block shear, 86.57 is what I obtained in step 4, 86, right? Was it? No, was it step 4? I can't remember. It was block shear was step 3 for beam, right? That was 88.76. Risa has calculated, and due to the some simplifications I did, right? A little bit, 86.57. So step 2, I did a beam bolt bearing on beam's web. That is 102.38 obtained here, which is 102 minus on web is 102.5, right? 102.5. So they're very, very close, 102.38. Okay, and then bolt bearing on clip angle, not at girder, at beam. At beam, it's this one. We obtained it, it's 143, right? We had it in step 5. Wow, 140. Okay, so step 5 we did it in, actually it's basically minimum of this and 143 and 140, so that's why it's 140 here. Okay, so I have verified the numbers also from the manual and Risa, right? Manual and Risa. My final answer is VRN equals to 88.7 kips. And what controls? Block shear. Block shear on web of beam. Of course, connection design is way beyond what I did. You have to check also the strength of the girder here, web of the girder. I have to check the strength of the clip angle itself against block shear and some other bolt prying and other stuff. Okay, but with this example, I hope this helped you. First of all, clarify the lecture we did last week. Second of all, you can apply all of these in Risa, verify your results. Okay, again, keep in mind, if you did this and step 4, I have done this, okay, bearing on bolts, the number you obtain is going to be 140.73. I want to write it so you know. If you wanted to obtain from bolt bearing on the angles, based on these, that's step 5, right? For this one that I did in table 6, that this would be just like similar to step 2, right? That would be, I have done it, is going to be 140.73 if you plug in all these formulas, right? Your LC1 would be 0.84 inches. So it's smaller than what's step 2, and your LC interiors is same thing, 2.19 inches. FY is 36, FU is 58. Thickness of the clip angle is 0.38 inches. So if you plug in all these numbers in just like step 2, but with those parameters, you're going to obtain VRN equal to 140.73, which matches with what you get in table 10.1 for this 140 kips. All right, that's all. And please for assignment for this class. Now repeat the same thing for your analyzed or designed member. Pick one of your beam to girder connections, all bolted, and check all these 5 steps for that. Thank you.